Okay, so while that's getting started, my name is Alex Wadell. I'm a fourth-year PhD student in Professor Venkat Vishwanathan's group, and I am involved in our MIST project, which, if you don't know, is an attempt to train a large language model, specifically a BERT style, on around 50 billion molecules, with the hope of coming up with an embedding that is able to achieve quantum accuracy, basically using a transformer. So the big question, of course, with that, I need to be a presenter, is it's one thing to say I'm going to train a model on protein as opposed. Oh, okay. I'm not here, right? Don't know. You go. Oh. Okay, so it's one thing to say that you're going to train a model on 50 billion parameters. It's another thing to actually do it. And the obvious thing that you'll hear to do, and I'm sure every PI you have has told you, is you just make the model bigger. And if you make the model bigger, the loss will go down and everyone will be happy and you'll just ride off into the sunset. And unfortunately, while that is somewhat true, there are some nuances to that. And today we're going to kind of talk about those nuances and how you too can take a model, make it big, and make your loss go down, but in a way that makes sense and is tractable. And tractable in the sense that it's going to still be very expensive, but it's going to be less expensive than it could be. So today we're going to have a little demo. If you want to follow along, I would recommend just following along and watching it on the screen. It's not particularly reactive. But if you do want to actually do it, you come over here. You're going to click this button right like that. And you have this wonderful.
So there may be new people. So can you just, I'll put you keep going.
Okay.
I'll put it on chat.
So the link is going to go into chat. We're going to be working through this notebook. It is if you haven't seen this before, it's a Pluto notebook. It's in Julia. If you want to run it, you can just click this wonderful little button, edit or run, and just follow the instructions. If you run into trouble, either message in the chat and I'm sure we can help figure it out. Okay, but without further ado, let's get going. Okay, so first off, as I'm sure we have heard before, transformers is a pretty transformative architecture in large part because it allows for the parallel evaluation of attention over sequence length, which allows you to do really, really big models in a way that is somewhat computationally tractable. Previously, of course, we were using RNNs or LSTMs, and because of that sequential dependence, scaling it up is not really a viable strategy. Of course, making something bigger doesn't necessarily mean it gets better. And the key thing that happened is Kaplan came out with this paper, neural scaling laws, that showed that if you increase your compute and your data size, and importantly, your parameters, with a particular ratio, your loss will go down and your model will get better. And then, of course, it's one thing to say that this is true, but it's another thing to actually show it. And so a couple months later, GPT-3 came out, their paper, and it got a lot better. And so this kind of really led credence to this idea that if you keep scaling up both model size and data, you will be able to push down your loss. And additionally, beyond that, we have the chinchilla paper. So Google came out with another paper where they basically said, okay, so yes, you can keep scaling it up, but it's important that you do it in a way that is compute optimal, because what you can have are these things called their iso-loss contours. So if we look at the amount of training flops that we spent relative to our model size, what we find is that there's these curves where you're going to get the same loss across the entire curve. And as you can probably notice, they bend up and away and down, and they have this nice little local minimum right here at a single point. And that defines the compute optimal frontier. And this realistically makes sense when you realize that training flops scales with both this number of tokens that you're processing and the model size. So if you make your model bigger, you are also probably going to have to spend more flops, right? And the key takeaway here is that if I, had a rather small model and I just train it forever, right, I am going to continue to see benefit. Like my loss is going to go down, it's going to get better. But if I just made it a little bit bigger and trained it less long, I would have a better model. And depending on the particulars of like how much data you use and how much model, how big your model is, depends on where you show up on this plot, and therefore how much budget you would have to spend to get to the minimum. But if you had a fixed budget, you'd basically want to say, okay, I'm going to come across here, I'm going to go up to this line, and that's how big my model is going to be. Now, again, it's a little bit more complex than that, in that, yes, there are coefficients that define this curve, but they're not fully published. Like Kaplan doesn't tell you all the numbers that you need to know. And second, it's not necessarily clear that just because one person fit a scaling law and they got this set of numbers doesn't necessarily mean that that's going to match up for your particular problem and your particular model and your particular learning rate scheduler. So you likely are going to have to fit your own set of coefficients and then figure out how you should scale. And so what we're going to do today is we are going to demonstrate how to do that. And just to kind of catch myself back up with what I'm showing in the slides, why would you actually care about this? Well, as they showed in the compute optimal scaling paper, is if you did just what, say, GPT-3 did, you get to that point up here. If you do what compute optimal would say, which is you adjust your ratio of models to data, you can actually bring that down pretty substantially. And instead of having to have a model that's this size, you have a model that's that size. So a couple orders of magnitude smaller, but more importantly, they hit the same loss. And if you'll notice, it's a bit cheaper. And as everybody has said, compute is rather limited. Academics are particularly limited in our compute, and yet we would like to have the best model ever. And so this is a strategy to be wiser in our expenditures. Okay, so what we're going to do, we're going to pull some data from Nicholas's paper, how to scaling laws in the data limited regime. Admittedly, in the data that I'm pulling from is not necessarily an appropriate source for this because they trained from multiple epochs and reuse data. The flip side is it's public and you can use it and I don't have to go make fake data for you. So we're going to be using that. If you've done your own scaling runs, use that instead. We're also going to be looking at how we can determine what is a compute optimal model. And then we're going to look at the limitations of this theory. There is unfortunately no free lunch. You can't make a model infinitely big and drive your loss down to zero, but you can get close and we can make estimates for how good of a model you potentially could have. Okay, so first things first, we're just going to grab that data. These lines are pretty straightforward. We're just downloading some files to CSV. It's pretty pre-tabulated. And we're just going to put it into a data frame. And I guess before I continue any further, are there any questions up to this point? No. Awesome. I'm not seeing anything on the chat, right? Oh, we do have things in the chat. Okay, we're good. So, anytime you're reading in data, it's always a good idea to kind of look at it. And so what we're going to do right now is we're going to plot what we got. So we can see that as our compute went up, our model size also went up. You're seeing these nice straight lines like this, essentially because what they most likely did is they had a fixed data set size and then swept their model size. And because as you increase model size for a fixed data size, your compute increases you get these nice vertical, diagonal lines across the plot. We can also see that, the theory that a bigger model, going up with more data is a better model, does hold. The points over here have lower loss than the points over here. But what we can also see is that other idea that just making a model bigger is going to inevitably make you better doesn't necessarily hold.
It's a GPT style models, right?
I believe so.
Okay.
I believe so. It would be necessary to check. I mostly just wanted data scaling. Okay, so what we're going to start off with is we're going to now fit a Hoffman et al.'s, so the Chinchilla papers, style of scaling law. Oh, hey, that's always fun. Oh, it's because I zoomed. Anyway, we're going to go down. Okay, so Kaplan had basically the exact same equation here. They had this A over N term. So this is how does your loss go down as you increase your model size? They had a B over D term. So how does your loss go down as you increase your data size? And then what Hoffman added was E, which represents essentially the fundamental intrinsic entropy of text. So essentially, even if you had a perfect model, you would not be able to predict the next token with perfect accuracy. It's kind of like if you're flipping a coin. We know exactly what that probability distribution is, but at the end of the day, you will never be able to precisely tell me what the next coin flip is, unless you're really good at flipping coins. So that's what E represents here. Now, we can see what all those parameters are and what they mean. And what we're now going to do is we're going to follow the procedure outlined by Hoffman to do this fit, which essentially results in us doing a little bit of transformation. We're going to replace our big A with a exponential of value, essentially to allow the little a to be between negative infinity and positive infinity. If we just had used real a, it would have to be, strictly speaking, positive, and that makes it a little bit harder to do your optimization. So we do a couple of transformations. LSE is the log sum exponent. So you take of each of these three terms right here, A minus alpha, B minus beta, and E. You take the exponent of it, you add all those as exponents together, and you take the log again. And then finally, we're going to be using the Huber loss. This is essentially a robust loss to outliers. So if you go outside of a region eta or delta, it starts having a linear increase in loss, as opposed to, say, if you did a mean squared error, where it would become quadratic and would be very sensitive to outliers. The downside, of course, of this is that you can't do really great statistics on it, but seeing as this is a nonlinear model to begin with, you can't really do statistics with it anyway. Okay, so for the actual optimization, we're going to be using the LBGF optimization algorithm. Again, following Hoffman, we're going to be using optimum to provide that optimization algorithm, using optimization from the scientific machine learning ecosystem in Julia. And then the nice thing, of course, is we're going to be using forward differentiation. So we're able to get gradients for our objective, and we can make nice quick steps towards that the best coefficient. Okay, so here's the code. It's pretty straightforward. We have a nice little helper here computing our LSE. And then we're just going to unpack our parameters, our data, and then our parameters. And then we're just going to loop over each one of our model size and data size. We're going to compute the Huber loss, tally it up, and return it. Very straightforward. Now, of course, because this is a nonlinear function, and nonlinear functions like to be annoying, before we actually just throw a gradient-based optimizer at the problem, we're going to do a quick little grid search. This is basically the range that Hoffman used in their paper. We can confirm that that initial estimate does lie within the box. So we're not like sitting at an edge and perhaps should increase the size of our box. But if, of course, for your particular data, you did lie on the edge of that search grid, you probably do want to do it. It is a little bit more fine-grained. They did a 0.5 step for alpha and beta. We're doing a 0.25 step. You know, play around with this. If you make it finer, it's gonna take a bit longer, but it is pretty quick. So we can show you that right here. So if we just hit enter, it's gonna redo that search, and there it goes. Okay, so that's all that happens. Hey, look, 4 seconds to do a search. Not too bad. Okay, so now once you have that, we just throw it into the optimization thing. If you're familiar with the scientific machine learning ecosystem, this is pretty straightforward. So you just create a problem, you solve the problem, you pull out your results. If you're not familiar with it, it's an optimization toolbox. It solves problems, relatively straightforward. And there's a link here to some documentation if you want to kind of do a deeper dive. Okay, so now what we have found, here, let's stop before we continue, is we have found our parameters. We now have alpha, beta, A, B, and E. So now what do we do with this? And before I kind of continue down that path, do I have any questions from the audience or concerns?
We have a lot of discussion to be done on the theory behind it and whether all of this, why this happens, but for now, keep going.
Yes. Have I included a link for that? I think I talk about that later.
Is there any special reason why first to LSE is wait.
I meant the theory behind neural scaling laws in general.
Oh, I know. Yeah, I know what you're talking about.
I'm curious for Hoover. I imagine you can like replace Hoover with any other reasonable loss, but why first to log some exponential to that?
Could you say that again?
Why do log some exponential to?
As opposed to doing
You just using the raw
thing.
Yeah.
I'm gonna guess it comes down to numerics. These thing is relatively sensitive. You're dealing with data wise, you're going over at least 6 orders of magnitudes in parameters and data size. If you look at compute, it's like even more because you multiply the two together. And the coefficients are relatively small. So moving it into log space and then back helps. There is a downside to that, which is that it's now become a nonlinear transformation. And so you almost certainly have a bias estimator for the actual underlying coefficients. The flip side to that is that it already is a nonlinear function, so you already have a bias estimator for all your coefficients. So like, and we're also using Hoover loss, which is not necessarily like a likelihood-based, thing. Yeah. So, how does that answer? Okay. Okay, so now that we have our fits, we can now estimate the optimal model size for a given compute budget. There is a fun little derivation in the appendix of Hoffman for this, but the high level thing is if you take that scaling law, you substitute in a value, the compute value, so say C is equal to 6ND, plug that in, and then solve for when the del of L over dn is equal to 0. You get these nice little equations for what your optimal model size should be and your optimal data set size should be. And the key thing is that they scale with some prefactor G and some exponent A. This is a different A and a different B from the A's and B's we were looking at earlier. I know, I'm sorry. The definitions are down here. So G is essentially looking at that alpha and that A relative to the B and the beta. And then A and B is the essentially how evenly matched is alpha and beta. So if alpha and beta, so if your loss goes down at the same rate as you double your model size and you double your parameter size, alpha A and B would be equal to 0.5. If it shifts from that, that means that you kind of need to scale up either your model size or your data size faster. Interestingly, Hoffman finds that A and B are approximately, or alpha and beta are approximately equal to each other, which implies that everything should be scaled evenly. Whereas Kaplan showed that the model size should be scaled up a bit faster. So they have an A of 0.73 is what they report. For us, you can see we're at a 0.68 to 0.32. Again, I wouldn't lean too heavily in this. We're kind of misappropriating the data because it did train for more iterations than we wanted to. We are kind of getting around that by pretending that we just trained on the unique tokens and ignoring the fact that we did multiple epochs. If you want to change that, you can come up to here and change that line right there, and it'll redo all the calculations for you.
Alex, this data set is, can you explain how this data set was generated?
The underlying raw data.
The one that, yeah, for your us, right?
Yeah. Okay. So for us, I believe it was training a GPT style model. And what they did is they looked at the data limited case. So in some data sets, you don't have infinite data. So what happens if you basically reuse that data, so train from multiple epochs? What are those scaling laws in that case? And what they kind of propose is essentially that you add a discount factor to your D and both the model size and the parameter counts to account for the fact that you're seeing these tokens multiple times, and the second time should be worth not as much. And if you do the two fits, so I'm basically just pulling in that data and calling it a day. And yeah, is that a whole, or do we want to talk more about, like, say, how do they generate the sweeps, or?
So that's the figure that you have on top, right? This plot raw data.
Yes. Yeah, so this is the actual data that they were running, that we were pulling in.
And this data was generated for
that paper, yes.
For that paper.
Yeah.
But you've done it for other.
I've done it for other systems. We haven't released that data, and so we're just kind of.
You're not showing that, but okay, yeah. but you have seen similar behavior, right? In
terms of these lines that we're producing. Yeah. So okay. So the reason that you see these vertical lines here is if you had a fixed data size, so say you were going to train on 100 tokens or 100,000 tokens, right? And you sweep your model size.
Yeah. Okay.
You're going to get that line.
Got
right?
it. So these data points come from Kaplan's or Hoffman's?
Neither. They come from Nicola's scaling data constrained language models.
Okay, so this
provide a notebook.
Okay, so and you take those data points and then so those are discrete runs, right? So every dot here, right, on that plot is trained to a certain model size, trained with trained at a certain model size and flops, and then you get the loss, and then from that you do everything else, right?
Strictly speaking, most of the time they're trained at a particular model size and data size, and then from that
you calculate a flops.
Yeah.
Okay, got it. Yeah, just make sure, right? Because this is not something that everyone sees routinely, right? So
yes.
so the workflow of how someone would go about doing this kind of compute optimal work, right, is so you have an allocation, right? And so you're going to train a bunch of small models, right, to be able to fit those coefficients, right? And then use that to then try to run, one or maybe, one or few production runs at
Right.
that compute optimal point.
Yes.
And so, so some of the things that you're pointing out now, right, is so if A and B, okay, so there's alpha and beta, right? So so you want alpha and beta, right, to essentially be as large as possible.
Yes.
Right.
Yes. So yeah, so to just kind of like run through what those mean, if alpha was really, really massive,
Yep.
That would mean that at doubling the size of your token or the size of your model, the size of your data is going to drastically reduce your loss. So it essentially controls, we go.
So it's the scaling exponent, right?
It's a scaling exponent. So if you did a plot of like model size versus loss, it's the slope of the line is alpha and the intercept is A. So A is basically how bad your model is with no parameters. And alpha is how fast it gets better as you add parameters.
Right. Yeah. So in this equation, right, that part is sort of lost because you sort of normalize beta by alpha plus beta and alpha. So A and B, right, don't actually tell you the speed with which the scaling laws are decaying. They're telling
Yes.
the ratio of how they're decaying with respect to data set size and model size.
Right. And there's a cool plot later on that is probably
Okay.
perfect for what you're looking at.
All right. Good.
So hopefully we haven't spilled the beans too much. But this is kind of one of the big things. So there is kind of like two notions of what is the optimal rate at which you should be scaling up your model and your data size. And to Venkat's point, this is why you almost certainly want to do a bunch of sweeps and fit your own scaling exponents. Because to go back to this plot from before, from the Hoffman paper, at scale, there's a very large difference between the top line and the bottom line, right? And there's a very big difference in cost. And so you want to make sure that you do have a really good understanding what your particular coefficients are and what the scaling relations that you are seeing. So that way you have the best possible chance when you do that one really big production run of getting the best possible model you could. Okay, so that's what we have. And this is how you kind of do the actual calculation for finding what your compute optimal model size should be. But now, of course, we're going to kind of take a step back here, which is what is the compute cost? This is kind of relevant if you're writing a proposal, which you almost certainly will have to do. So we've been talking about compute and the cost, but what do we mean by that? So the key thing to remember is it's not the wall time, it's not the node hours, it's none of that. It is the number of floating point operations that would need to be performed in a forward and then backward pass of the model. And there's a very detailed, step-by-step process in the actual Kaplan paper for what this cost is. But at a high level, you can think of in the forward operation, each parameter is involved in two floating point operations. There's a multiply and there's an accumulate. And in the back pass, you have to do a multiply and accumulate to update your parameter and a multiply and accumulate to update your optimizer. And so you ultimately end up doing around 6 operations for every parameter in a forward and backward pass. And then you have to do that for every single token. So it's 6 ND is your overall compute. Is this a really great model of floating point operations? No, it is not. There are additional terms, like you could account for the fact that you have embedding parameters. You could account for the fact that some parameters cost more. So you do, like your attention parameters are used a little bit differently. The actual aspect ratio matters. But when you're talking about trillions of parameters, this is a leading order estimate, and it's good enough. Okay. And once you've done all that fun stuff, you now get a plot like this. So your very own set of ISO loss curves. And what we can see is that, we have this nice little curve. So if I train this model, for example, we can see it's very far from the red compute optimal frontier, right? So realistically, for that budget, if we had instead made the model about an order of magnitude larger, we would be much closer, even though we would train it on effectively less data, but we would get to a lower loss. So why spend more compute when you can spend less smarter? So if you stay on this nice red line, you can be happy. The caveat to this is that what I basically have told you is that if you had a compute budget, and hypothetically you could actually realize it, that all you need to do is increase the number of parameters in your model, and now you're super happy. However, as anybody who's tried to actually do a thing knows, that doesn't always work. So there is a fundamental limit due to the fact that this is a language. Even if you had a perfect model for flipping coins, at the end of the day, the next state is a 50-50 chance that it's either. And so there's this fundamental entropy in the system you can't get better than. There's this really cool paper from quite a bit ago that actually gets into this stuff. So they look at the case where you have a asymptotically correct model. So a model that with infinite parameters is capable of resolving the true distribution of the system, as well as a model that is incorrect. So with asymptotically large number of parameters, will never converge to whatever that true distribution is. And what they do actually come up with a thing that basically says alpha should be 1 under a whole bunch of assumptions. But it's kind of nice to see. So just to put a little bit of a practical example to this, if we look at English, the Shannon entropy is around 2.6 bits per character. So realistically, you can't go lower than that because you never know if someone's just gonna be like, ah! And then you wouldn't be able to predict it. Okay, so Hoffman has modeled this by adding this E, which is your minimal loss. And if we then take account for this E, we plug in our compute optimal values for N and D into our loss equation, we can find out, given a particular budget, what our loss should be if we did everything perfectly. And we fit our model perfectly well. A bunch of caveats. This is how we do that calculation. Gets a little bit messy, but it's not too bad. And here's what we find. So this initial slope right here, this is kind of looking at that. Essentially, this would be for, in this case, we're essentially looking at A. So this is how much better your model is going to get as you spend more money on it initially. Now, unfortunately, because we have this E term, eventually it has to flatten out. There has to be a plateau. And we find that we do plateau. And we can kind of also see this in the data, right? So in theory, every single point on this curve should lie above the red line because that would imply that we had a perfect fit. We don't obviously have a perfect fit, but we can see that it is correct and that it is generally points are lying above it. Right? It is setting up a good lower haul on what possible losses for a given budget. And we can also see that if you did draw just like a straight line, right, from the initial points, you would kind of expect it to be down here at this point, doing quite a bit better than it is. And so we are seeing that curvature that the existence of E suggests. Now, the other, this is a bit sad. It does mean that we can't know everything, and eventually there will be a limit to how good our models can be. The flip side, though, is we have a lot of runway. In this particular case, we can see, we have to go up about 5 orders of magnitude before we really start to flatten out. And so there's probably a really good argument to be made that making this particular model significantly larger makes a lot of sense, and there'd be good gains to be had. Okay. And so, yeah, our main takeaways, of course, is that we can do this. If we do this right, we can be more efficient. We can go better. Got a question? Go back up there.
Yeah, has anyone tried to derive like what these entropy limits are for like other problems? I mean, you could imagine, I mean, and I don't know if Arvind or anyone from Arvind's team is listening, but I mean, I think I could imagine that, something like their genomic sequence model, right? You can actually like pretty reliably like derive these entropy limits.
Maybe. The problem is you really have to account for the full joint probability. So you'd have to account for all the previous things. Essentially, you have to build a language model for your language to then figure it out. And so they probably can actually come up with at least like the Shannon entropy, where you look at the frequency to get a number.
They are probably the only field where you could actually like come close, because if you look at like the molecular foundation models, right, like there's very little insight in terms of, we have a smiles representation that is already a lossy mechanism. And then you have, tokenization of those.
Yeah.
Versus sort of, genomic sequence models where at least, they're like, biology is conveniently tokenized it for you, right?
Yeah.
So I think it would be interesting to, interesting to sort of tease that out. And I think if you, and maybe something that, we tease out in the hackathon, but Arvind's team has trained a lot of these kinds of models, right? It would be actually very interesting to just run this kind of analysis on their data to like see what that number is. And then from that, you can at least back calculate what the, what the Shannon entropy limit is. And then you can then, from there, guess, right, what sort of the intrinsic entropy is.
And maybe just to clarify there, that E value is lower than the Shannon entropy. So the Shannon entropy assumes that every single thing is.
Yeah, of course, right.
Just wanted to.
Yeah. Yeah. So the E that you would, it would be good to know what E has been empirically observed, right?
Yes.
From all these models.
And I guess.
And I think that also gets to the heart of, some of these questions that Karthik has been asking, right? Like if that fundamental E for these models, right, is not better or not that much different than other, physics-based regressors, right? Then that's a problem, right?
Right.
That shows that even if you sort of, through all the compute you had, through all the data you had, right?
It doesn't.
Then it doesn't matter, right?
Right.
And so it'll be useful to understand what the E is for sort of these various kinds of foundation models.
Yes. Yeah, no, I think you're hitting on like some really big points here, which especially because if you kind of don't account for this, you'd assume that you could just get better forever. And realistically, that's not necessarily true. And the other really nice thing about this framing is if your model is small, you probably are going to see a really low E because it hasn't started to curve yet. So it doesn't really know what a good estimator is for that E value is. But as you get more data, you would learn and you would get better.
Yeah, and I think this gets to the heart. I mean, the E term is actually not very well appreciated in, especially at least, we're far from that E in the language space because,
People can say random things.
yeah. So so there's a lot there, right? But I think we might approach closer and closer to E, right, for these kinds of scientific foundation models, because the number of possible, useful data, right, useful tokens, right, we might be able to exhaust pretty quickly, right? And so it would be, interesting to understand, what that is, and I think, we should absolutely try to, in the hackathon, try to run a few numerical experiments with, or maybe Arvind's team has already run it with GenSLM, but try to bring this framework and that together, right? And see, if we can tease some of these issues out.
Yeah. And I guess, is anyone on Arvind's team, do you guys know what the Shannon entropy is of DNA just off the top of your head? I know that's kind of a random question, but figured I'd ask. Probably no. Yeah.
I don't know if they are there, but I mean, I would like to construct a fake universe where I know everything.
Oh, but ultimately, if we believe that this is a probabilistic distribution, right? Even if I know that distribution perfectly.
No, I know.
Yeah,
that.
yeah.
No, I'm talking
Yeah.
about setting up the problem.
You're just
and
E is
answering.
0. Yeah.
Instead of working in real problems. But yeah, keep going. I think we should have a discussion. We have Mike, who has looked at some of this for PDEs, some scaling laws that he's explored. Is that the last slide or?
No, so we actually have another slide here,
Yeah.
which is specifically because of your comment this morning. So I figured we'd talk about this. So to those who weren't here, Karthik got this question, 512 parameters for an embedding space is huge. That's like a crazy regression. And I kind of made this hand wavy comment that like, oh yeah, but like if you make your model big, you kind of need to make it wide as well. And here's the proof in the pudding. So this is coming out of the Kaplan papers. So they did sweeps over three different shape ratios. So the first one is the feed forward ratio. This is the number of channels in your feed forward wire in a transformer. So per channel in your hidden state, in your embedding space. Generally, this is about 4. It's either around 4 or 1, seems to be what everyone has consolidated around. You can see that it is relatively sensitive to it. So if you're at a feed forward ratio of 1, you're around that minimum, you kind of bring it up a bit, you're still okay. But as you start going beyond, say, 10, so having 10 channels in that feed forward for everyone in your embedding space, your loss drastically starts going up, okay? The good thing here is that it's pretty easy to keep your feed forward ratio constant as you scale up your number of parameters, right? You just double your embedding size. You also have to double your forward space. The other two are a bit harder to hold constant. So your aspect ratio is the size of that hidden dimension divided by the number of layers that you have. So this tends to sit in the range of 64 to 128. You might notice those are powers of 2. People love powers of 2, so don't spend too much time thinking about that. But you can see that they show that it does get bad if you go too wide. If your aspect ratio becomes either too slender or too fat, it's not so great. But there is a pretty wide margin in which everything works, which makes it a bit easier to kind of scale things up. And then finally, we can see in attention heads, it's pretty much flat. So if the size of your attention head, so that's your hidden size divided by the number of heads, as long as that's somewhere between 64 and 128, and you'll notice that it usually is either 64 or 128. This is because you basically need to have nice multiples of usually 32 in order to make everything nice with CUDA cores. Everything works out. I'm right now here listing some ranges for what I've seen in the literature. I think this is based on, let's call it 10 or so papers so far, 10 different models. I wouldn't go out and, stake my life on this, but if you're outside this range, think about it. Do your homework and be smarter than me, which you should do in general. Okay, there's a couple of exercises to read here. You can do Kaplan's method, which is really easy. You just get rid of that E. You can do the data sparsity thing, which is a little bit more complicated. You're going to have to add a discount factor for your D and your N, but relatively straightforward. So it goes up in the loss thing. And then, of course, the most fun one is if you have your scaling data, or for example, your Gen SLM and you want to give it to me, do this whole thing again for your data. Any questions, comments, or concerns? Oh, and then, of course, if you're confused about how to run this, there's some stuff about Julia and how to get it where we're going. There.
Yeah, one is first open up, I have a few high-level questions, but I want to see if people want to add comments. Or first of all, do people have questions about what Alex was presenting? This was neat, by the way.
It's a cool.
I mean, I've seen papers, I've seen curves, but
yeah.
Correct.
Yeah.
But yeah, to bring it as part of the process early on.
Yes.
And including that, in your dashboard is something we should all do.
Yes.
But anyway, questions from the audience?
The other nice thing about doing this early on is then when you inevitably spend several thousand node hours in a weekend, you can at least say, yeah, but I did my homework. I didn't just burn $1,000 for the heck of it. So it's helpful because at least when we're scaling these things up, it can become, there's so many parameters to sweep over.
Did you do anything like this for MIST?
We're actively doing it.
So are you seeing anything like this?
Yes.
Okay.
Yeah, it's very helpful. Makes me significantly less stressed.
Okay. So so Mike, you've explored this for PDEs, and at least in your limit, it seemed to be not saturate at all, right? There's a long way to go for the range of problems you looked at.
Okay, can you hear me? I can't do the video, which is fine.
Yeah,
I mean,
that's fine.
I mean, I think it's hard to say. I mean, I think probably the leading order thing is that existing models that are popular, like what's it called, the forecast net and stuff, don't have the capacity to get this over orders of magnitude. They tend to saturate. So I think it's an open question what a general model is that would be able to absorb data and compute and sort of write the same way. Yeah, I mean, and presumably that's because of constraints and other scientific things. It might just be sort of other stuff, but yeah, I don't think they have. I mean, that means that you're going to need some sort of new architectural advancement beyond. I mean, maybe transformer plus plus, but that's the models seem to saturate. They don't, because in a sense, what you're having is a protocol where you scale model and data and compute. But when you scale data, there's it's quantity and quality of data, it's type of data, it's et cetera, and the quantitative value of all these exponents would be different depending on how you did that.
Yeah.
But most of them
Yes.
seem, if you put them on a log plot, they do fine, and then they saturate somewhere, is I think the bottom line. So there's, yeah.
Yeah, there's so many variables here. So I know it's probably not possible in continuous domain problems, but my interest here is, can we design a toy problem with finite alphabets, but big enough? Maybe we're going to waste a lot of compute, but still, can we answer this question a little more rigorously? Can we like set up a fake biological problem where the universe is completely under our control and there are some simple rules we can play with, and then approach
I
it
mean,
with
why
a-
do you, why the distinction? Why do you say you couldn't do it with continuous? I mean, I know entropy of 0 and negative infinity, but you're not talking about that, are you? You're talking about something else?
Yeah, I mean, I know continuous, first of all, of course, there's some issues in how you define things, but also I have just no faith in a continuous universe in being able to represent it with these kind of things. I think we can do that with some linear Gaussian or something, but I'm okay. Continuous, discrete, it doesn't matter. Thinking of a scenario where we control the rules and then we show that these things have some merit.
The paper I linked that does the theoretical stuff is probably a good place to start, because that is like a 1984 paper, so it predates basically all the cool tricks we have now
Yeah.
by quite a bit.
Yeah, I know the
It's
guy,
small.
the first author was the one who invented, or is the main person in information geometry. I know the
Yeah.
person.
I mean, I think the reason I asked about the continuous is I think the continuous to discrete transition is sort of an important one, right? Because what you do in continuous vision is different than in discrete language. And the tokenization buys you a lot, but there's just a lot of little things. I mean, the best analogy I can come up with is, a lot of people, you wouldn't do sophisticated aerodynamics or whatever with the Euler's method for discretizing anything, right? But that's the 101 thing you'd cover in the first chapter of a numerical analysis book, right? And so there's just a lot of more sophisticated ways that are Euler plus, volume, finite volume, and a million other things. You get the discretizations to cancel the right way, et cetera, because nothing on the computer is continuous either. You got to be careful about the numerics.
Right.
So I think getting the embedding, I mean, I think the existing theory is like a little too coarse to modulate that discrete to continuous gap, but understanding how the tokenization would relate to something continuous, so think of subgrid resolution, right? You'd like to scale down to subgrid. It doesn't mean that the tokenization that works discretely would work at all for that. So I think there's a question, the DNA question, can you have a discrete universe and control everything? More broadly for scientific ML, I think understanding that discrete to continuous is probably important to get the scaling right, and at least have it behave gracefully when you go subgrid, to something below the discrete level. Because there's no notion of geometry, whether it's a 1D time, think of you doing a forecasting, or a 2D space with the tokens, right? So that's a separate mapping or concept altogether.
Yeah.
And so whether you call that a transformer plus, something transformer like that has it grafted on, or a different architecture is sort of, which, your prior where you come from. But I think that's likely an important thing for understanding the scaling.
Are you aware of anything in this for just like even like a simple network? Because like naively and like having and training these things, it feels like classification is so much easier than regression. In that, like really with classification, you just have to put a hyperplane. There's really a ton of hyperparameter planes that realistically are like okay. Whereas
Yeah.
regression, you kind of have to hit it on the nose in order to be good. And I haven't like that's been like a vague feeling of mine is that regression is harder. But I haven't seen anything to say, yes, that is in fact the thing, which does seem to be like what we're getting at here with that continuous to discrete transition.
Yeah, I mean, I think in a lot of cases regression's harder. And again, I guess the capacity control you get with discrete things is sort of qualitatively different than you get with continuous things, right? Discrete things, you'd get a log n approximation or minimize a cardinality or something, you know, but what you get with continuous things is not that, right? In functional analysis, you'd bound norms and stuff, right? And so they are different. And I guess I don't know how different they are with respect to this discussion, because if you take a classification or regression model and you squeeze it, you know, hard, you know, I think the key issue is sort of when you know, if you squeeze it hard, how do things behave? And you know, think of like a ridge regression. If your ridge parameter is 0 or goes to 0, things are qualitatively different.
Right.
Because the more Penrose inverse sets the whole complementary subspaces to 0, but the ridge parameter would say if it goes down to something very small, the inverse 1 over it becomes very large. And so controlling the way, you know, that soft regularization becomes a hard constraint seems to be sort of a leading order thing here. And I don't know that the information, I mean, the way they frame the question, it doesn't sort of seem to answer it, and the way ML frames it. So I think, but something a little bit finer touch there in terms of that discrete to continuous mapping is sort of like doing a higher order integrator in PDEs. I mean, it's getting something like you know, a graceful behavior as some parameter becomes small. And I think that'll be important in particular for the scientific models, because you know, if you're modeling the climate or whatever at grid 100 kilometers on a side or 25 kilometers on a side or 10 kilometers on a side, you don't want it to, yeah, you may not expect it to get better when you get smaller, but you don't want it to just become terrible and feeding. If you're not very careful, it becomes terrible when you go off grid, because there's nothing in the ML training process that knows about the underlying continuous structure.
Yeah.
Yeah. And Michael, I think I remember one point you made in the conference in April that if you take the weights of the neural networks and you plot them, they look very different now than they looked 10 years ago or something, or 15 years ago. And is there any reason to believe they won't look the same in 10 years from now? And how does that impact some of these scaling discussions?
Yeah. Yeah. So if you don't know what, yeah. So it's
yeah. I think in your own words, since it's just not you and I talking, if you can just go through that concept and idea, and then
yeah. So a slight refinement on that. So the question is, say that you give me a model and I don't know how you trained it or don't know anything. Could I just look at the model and learn something? And this is what Wigner did when he studied nuclei, right? He wasn't small enough to go inside a nucleus, so he said, I'm only going to look at observables. You know, I'm going to scatter the nucleus, and I want to work on Z equals 92 nuclei. So I'm going to do random matrix theory and just look at low-lying states. So, you know, if you're training a model with a gazillion parameters and you're not going to give me all your data, et cetera, I want to look at the model, namely something that's falsifiable, and analyze it and try and come up with something. So a 10,000-foot view is that every model that's sort of small, as a toy, you know, think of pre-2013 when you got the inflection point in machine learning. If you looked at the eigenvalues of the model, not the weights, the eigenvalues of the weight matrices, they sort of looked like bulk plus spike. There was a bunch of stuff that was consistent with random and a few eigenvalues sticking out. Everything post 2013 is not that. It's heavy-tailed. You know, think of it as power law. It's not always that functional form. The weights themselves are not heavy-tailed. It's the correlations that are heavy-tailed. And that's important because I think you should think of these models as strongly correlated systems, not some random thing, of course, right? And so you're moving out of a Gaussian universality class, which is what a lot of the theory is framed as, and away from a bulk plus spike model, which is a low rank perturbation of Gaussian universality class, to a heavy-tailed universality class. And so things are much sort of harder to deal with. But there is good reason to think that, it'll be at the same 10,000 foot view, the same in 10 years, right? You're in a universality class. It's very broad and robust, and if you're cooking in more correlations, that should come out sort of more cleanly. So I suspect that this will stand the test of time in that sense. A different way to think about this is, what if I had university scale compute, or even more than this, I just had the laptop in front of me, so not even GPUs. So it's not that I had $100 million with a computer, 100,000. I just had the GPU in front of me. What could you learn? And one answer is just chew on the matrices, the weight matrices in publicly available models. And could you learn something about chinchilla scaling or any of these scaling things? And the short answer is yes. Pre-2013, it was Gaussian universality. There's no scaling, it was bulk plus spike. And the heavy tail on the eigenvalues is the empirical manifestation of this scaling stuff when you don't have obscene amounts of compute, when you have your laptop. So you're seeing this in the structure of the model. And so what you're referring to is, it's not the weights themselves, it's the correlations in the weights and the eigenvalues. And you see, this is a pretty ubiquitous property, and it's very sort of descriptive, I think. I don't know how it relates to if you have a moderate amount of compute like this talk, and that's maybe a future question to ask, but that's what you're referring to, yeah.
Yeah, thank you. I think if for our benefit, if you can, by the way, you can share your video and screen if you want, but if you can drop maybe a reference that we can look at for what you just mentioned, it's super interesting.
Yeah,
I think
I'll give two, one that works a bit through sort of the ideas, and one that solves a practical problem, like predicting trends in model quality without access to any data. No training, no testing data or anything. So I'll put two things. You want me to put them in the link?
Yeah, put it on chat.
Yeah, I'll do
Put it
that.
on chat, so I think all of us can use it.
Yeah, and the idea behind if anyone reads the papers, follow up with me if you're interested in or care or anything. The idea there is basically, imagine, you can't do quantum mechanics on a protein or DNA or some huge thing, right? But you still, the quantum mechanics is motivating what you're doing. It's a guiding principle, right? And so you're coming up with essentially a semi-empirical theory, like was used in nuclear structure theory or in quantum chemistry or in fluid dynamics. So you have a theory that is compatible with the underlying theory, but where there's a big sort of, and then the magic occurs gap that you parameterize semi-empirically. And I think that's probably a good way to frame theory for these sorts of problems, because existing ML theories, there's a pretty far theory practice gap, but doing something semi-empirical is much more plausible to my mind, I think.
Yeah, agree.
Just a quick follow-up question. The transition in the eigenvalues of the weight matrices, do you know if that's like correlated with like model size, how the architecture, how they're being trained?
Yeah. Yeah. So, yeah, give me an hour or two and I'll tell you. So it's a long, complicated story. The short answer is
Okay.
The short answer is everything post 2013. The long answer is obviously longer.
Okay.
What I think the scientific models here provide an interesting case because so this is a statement about the world, right? This is not a worst case theorem. This is a statement. There's a theory, a predictive theory here, but it's a statement about what's released in the world. And this, if you look back in 2018, there was 10 models available. In 2020, there was 100. In 2022, there was 10,000. Now there's 100,000 models out there. So what models are out there? It tends not to be great models for cosmology because there's not such money in cosmology, right? It's good models for classifying cats and dogs. So it's a lot of internet and social media stuff, CV and NLP. And the idea is good engineers tend to push out good models, but they're subject to the own quirks of the business cycle. So think of this like a natural experiment. You're looking up at the sky and there's a selection bias on what stars you see. So for models that are large and good for production and good for real practical problems, that's biased towards industry scale, but the same sort of things that I'm pretty confident would hold for scientific things done differently in detail, of course, right? You tend to see this sort of strongly correlated property. The training process is designed to squeeze out correlations, and you see that in the eigenvalues. Bigger models are oftentimes better, but sometimes if they're so big that you are forced to undertrain them, sometimes they're less good by these metrics. And so there's a non-trivial trade-off space in the sense of this sort of scaling, right? And so you could ask what's the best value for those exponents, the metrics that you pull out of that. So we have some ideas how it relates to model size and model width and other things. Yeah, certainly.
Might have to start doing computing eigenvalues. That's what I'm gonna go do.
Yeah. So lots to read. So Michael, but just drop a couple of papers in chat and yeah, take a look.
Yeah, so there's two.
Yeah. Great.
And I think it complements this. I mean, I think if, you know, there's an interesting point. If you have, I mean, these papers we did a couple of years ago, these are if you have laptop scale compute, right? On state-of-the-art models. I mean, these things work for, you know, more recent stuff, GPT-4, et cetera, right? Except it's a little different in terms of, do you have the weights versus API access? But when you can compute things that are moderately large, but not obscene scale compute, like these scientific problems, presumably there's a large space to go between this, you know, stuff that involves very little compute, but a lot of thought, and the other stuff that involves very little thought, quality of science, and just lots of compute, you know, so.
Right. Have you looked at, or do you know anything about like how the eigenvalues change over the course of training? Because you mentioned, you know, that there's like some impact on like early or over or under training the models, which I mean, compute optimal kind of suggests you should do.
Yeah, so the previous claim was a static, call it a static claim, right, at the end of training. Of course, the end is just when you got tired or pushed something into production or submitted to a public, you know, so there's not a principled end, except you just got to get it out the door.
Right.
The dynamics of training is a little bit more non-trivial. So now you need to either have access to data where there's checkpoints, there's a few examples of that, or compute yourself. So the dynamics is a little bit complicated. I think the short answer is, you know, early there's an explore and exploit phase, and it roughly parallels what machine learning people would mean by it. And in the explore phase, you tend to pull out a few eigenvalues. And so you might say it's a low rank, or there's a low rank space. There's papers out there that say there's a low rank space that dominates stuff. But you tend to choose. So you could imagine training with very small step size or lots of epochs, and you know, pulling the eigenvalues out so everything's nice. But you know, you could also imagine that doing that's a lot, you know, it's pretty wasteful. You might as well cut the step size in half. And so the annealing schedule for the training protocol is a parameter that's like this scaling, right? So you tend to scale that in a certain way, decrease that at a certain rate. So you're not being too wasteful on compute or other things. So in particular, you don't pull all the eigenvalues out and then do something. By the time the eigenvalues start to pull out, namely leading order correlations get pulled out, you don't pull them all the way out. You tend to basically change learning rates or other parameters so that you can squeeze finer correlations out, because that helps with mean squared error, perplexity, or whatever. And so you tend to pull those out before the other ones become fully out. And then so you can imagine you iterate this process and there's a get richer phenomenon and you get a heavy tail there. So that's a short answer. The slightly longer answer is if you have a model with a big layer next to a small layer, the big layer might be easier to train quickly, and so it gets to some metastable state, and the smaller layer takes time. But when the smaller layer gets better, capacity gets sucked into it, and the big layer gets worse. And you know, it's a rather complicated dynamic sometimes.
Oh, thank you. We're recording this, right?
I think we can spend the next 2 weeks
Oh,
thinking
yeah.
about that, but
Yeah. I have. Oh,
we're gonna, even for some of the models you're training.
I have
it'd be nice.
traces of checkpoints.
Yeah.
We can do this slide. I have a whole CPU that's just sitting there doing nothing.
Yeah.
Might as well compute some eigenvalues.
Yeah, let us know. We could follow up. I think this is, and Kareem is there next week, if not now. So
Right.
this is an obvious low hanging fruit to.
Oh, yeah.
action.
Yeah.
Yeah.
That'll be good.
Cool.
Okay, any other questions or discussion points from anyone else? Oh, yeah. So whoever is local, please, if possible, please show up to the FXB building. We can take a group photo near the wave field. So whoever's from we're going to meet there in about 25 minutes. But everyone else, thank you again. So we have one final day of tutorials and talks, and then, we get into hacking. So thank you very much for attending. And thanks, Alex, for, we spoke about so many things that are more fine-grained and detailed, but this is something to pay attention to as well.
It's fun.
Yeah, thank you. Bye.
Thank you. Great.